where we ended was why on earth, or we said that this was just kind of bizarre to be able to get the nitrogen on the ring first. First and foremost, that was bizarre because nitrogen, typically being the third most electronegative element, should show up as a negative charge. And if the ring is going to form a bond with that nitrogen, that would then mean the ring would need to be positive, which is counterintuitive because the ring has tons of electrons. So we would need the nitrogen to not have electrons. And the only way the nitrogen doesn't have electrons is we attach it to something that is more electronegative in it. Okay? And that's the oxygens. So we end up forming the nitronium electrophile that can go through and react, and then that puts the nitro group on the ring. Okay? So we do get the nitrogen attached, but the chemistry isn't set up very nicely there. Because what that ends up doing is putting a positive charge next to the ring. Electron density is now drawn towards that positive charge. It's not now able to leave the ring. So we couldn't do, say, another reaction with this structure. Okay? So the question I believe we ended with was that if we look at the nitrogen, we said what is so special about the nitrogens in the final product, the NH2s versus the NO2s. The NO2 was positive, the NH2, the nitrogen, is neutral. Okay? The big reason why that's super important is that with the nitrogen being positive in the NO2, we have deactivated the ring. That electron density is stuck in the structure. It can't actually leave to do a nucleophilic attack. If we move to the NH2, because that nitrogen has a pair of lone pair of electrons, those electrons can be donated into the ring, thus putting negative charge on the ring. Now the ring is actually a better nucleophile. So a subtle change in the oxidation state of the nitrogen, going from it being fully oxidized to fully reduced, now drastically changes the reactivity of the ring. Okay? And that's going to come back when we talk about the activated versus deactivated aspects, which is kind of what our lab is about today too. Okay? So we've now got the nitrogen on the ring, and we can now say, okay, well, what could we potentially do with this? Kind of like what we would do with everything else. Okay? And that's where we encounter the next reaction. Okay, we take sodium nitrite, so NaNO2. We just had an NO2, so that's a little weird. And an acid, and I react that with my nitrogen structure, and then I add a copper bromide, and now all of a sudden the nitrogen's entirely gone and I've got a bromine on the ring. So I'm doing a substitution, but this substitution is a little bit different than what we've discussed already. Okay? In our previous EAS substitutions, what were we doing substitutions for? Hydrogen. Here we're not doing a substitution for a hydrogen, we're substituting out, at least as this is drawn, apparently that nitrogen, okay, the NH2. This can give us the freedom to do a variety of more substitution pieces. And you might look at that and say, well, putting a bromine on. Did we have to do 4 steps to do this? Okay. Because remember, if we started with benzene, okay, first we'd have to take our HNO3 and H2SO4 to get to our nitro. We would then have to reduce that. We would then have to add our sodium nitrite and our copper bromide, and then we'd have the bromine on it. So I did 1, 2, 3, 4 steps to put a bromine on the ring. Can I do it in 1? Yes, I can do it in 1. Ooh. What could you do it with? See, but if you'd answered yes and then say, but I don't know what it was, then you put the position on me where now I have to answer you. But because you didn't answer and ask the question, instead you get me answering and asking the question. It's not a bad idea. You'll probably just get me saying I'm not going to answer that, but you can always try.
Could you do like the BR2 and then the iron bromine?
Bromine is an electrophile, okay, when it's bonded to bromine. BR2, there's an electrophile. I could do that in one step. So why on earth would we do this? One step versus 4. Okay. The end result here ends up being a little bit bizarre because we look at this and we just say, well, that doesn't make sense. I could just do that in one. And yes, in this case, we could do it in one. But what happens if we have to run other substitutions? Okay. Those other substitutions are going to be affected by the substituents that are on the ring. Okay. So the choice of which one we use may very well come down to where we want it to be located around the ring and where we want to do that substitution. So having the freedom to do different or do the same reaction but different ways, even if they have multiple different steps, could indeed actually be helpful at some point in the future. Okay. Where this is more relevant is not so much putting the bromine on the ring. Okay, so if we backtrack here a lot, I'm going to regret this. Sorry. Damn it, it's not on there. What? Oh, I know. Because there's so many reactions that it's not backtracked, it's actually on its own slide. Dang it. Sorry if you're getting sick watching at home. So, that happened kind of fast. Okay. I could put on a chlorine, a bromine, a cyanide. Okay. We haven't talked about being able to put a cyanide on the ring yet because that's going to be a hard one to directly do in EAS for because what charge is the carbon? Negatively charged. I wouldn't be able to do that. Okay. The iodide, fluoride, that's kind of a bizarre one. We haven't seen F2 reacting with anything. We did briefly talk about why we don't see F2 reacting with anything way back when. Why not F2? Not quite. No.
It's small.
It's small, high electronegativity, goes actually to its reactivity. If you look back at the radical reactions, we really only had one radical substitution reagent, BR2. That was the only one we used. We said we could do Cl2, but Cl2 wasn't selective. It would react with any hydrogen. Right? It would at least do the reaction, but it would react with any hydrogen, and it wasn't very good. But it reacted faster than bromine. Well, F2 reacts with any hydrogen as well, and it reacts even faster than chlorine. It reacts so fast that it usually results in a massive explosion. Okay? F2 as a reagent is not a fun reagent because it is dangerous, right, and causes big explosions. So we haven't seen F2 show up very frequently. This is a case where we could put fluorine on. Okay? Notice the next one. We have OH. Why is OH a weird one to put on? Again, that's a negatively charged oxygen. Okay? Nitrogen was hard to get on the ring because nitrogen is typically negative. The way we got nitrogen to be negative or positive, attach it to oxygen because oxygen is more electronegative. How can I get an oxygen attached to the ring? Why did somehow have to put fluorines on the oxygen? Preface our previous conversation 5 seconds ago. Fluorine causes explosions. That's not going to be a fun reagent to get the oxygen to be positive to react in an EAS fashion. So I can now get an oxygen attached to the ring, but I have to follow through this sequence of reagents. Okay? The last one, even more interesting, is putting a hydrogen on the ring. Okay? Didn't you just undo everything that we were trying to do? Yeah. But is reversibility something that's potentially useful? Yes. So there are cases where we may want to reverse a reaction. I can now reverse by going through this process. Okay? The big deal here is not the carbon-bromine back in our steps up above. Step 2 is ultimately irrelevant. Step 2 is what we're saying we can do in all of these other sequences, that bottom massive collection of things. Those are all step 2 reagents. The important part that is trying to be addressed here is the formation of the Benzenediazonium ion. That reagent is, or that product is coming out of step 1. Okay, so we now know the product. We're somehow forming this triple bond nitrogen. Why would that triple bond nitrogen be so useful in the step 2? Why would all those step 2s now be possible? What do you see in the benzenediazonium? We have N2. We have N2 gas. That is a phenomenal leaving group. So if I can make that structure, I then just need the proper kind of catalyst. That's where the copper comes in most cases, to help initiate and almost couple and kick out the nitrogen gas leaving group and slide on the other piece. Okay? But I still have to get that piece. Okay? So how do we get it? Well, that means we got to go back and look at our reagents for step 1. What was our reagent for step 1? What's the most reactive thing there? What? The BR. So if I threw HBr at you, you're going to freak out about the BR? Let's switch it up. Let's say it's not BR. Let's say it's Cl. I threw HCl at you. You're like, oh my god, chloride. What are you freaking out about? The acid part of that. Okay, it's the hydrogen. It's the HBr. Okay, the halide on its own isn't a big deal. It's that acid. It's that H+. So I agree that H+ needs to get neutralized as quickly as we can. What should I neutralize that H+ with? Electrons. Good answer. Which electrons? Where are there electrons?
There's
A negative oxygen connected to that nitrogen. I don't know. We have Na plus and NO2 minus, right? Remember when we looked at NO2 before, it was NO2 plus? Interesting, this is not the nitronium ion. This is a different species. This is NO2 minus. And we're now running into this dilemma. Well, where's that minus charge? Well, how would we figure that out? Yeah, we need to draw the Lewis structure. Right? How many electrons does nitrogen have? 5. Oxygen. 6. There's 2 of them. To have a negative charge, what do I need to do? Add an extra electron. So I get 12 plus 5 plus 1, 18 electrons, right? Nitrogen will be my center atom. I'll put my 18 electrons in, starting with the oxygens. Why starting with the oxygens? They're more electronegative. Then I'll put the last pair of electrons on the nitrogen. Oops. Then what do? Are there 18 electrons in that drawing? Yes. Okay. So now what do? So we need to make sure our octets are satisfied. Do the oxygens have their octets satisfied? They do. Does the nitrogen? No. How do we fix that? We make a double bond. Which oxygen do I make a double bond with? Either one, because I have resonance as an option. Okay? Now I have a structure. Now what do? Assign formal charge. How do we calculate formal charge? Oh God, that was so long ago. That is so long ago, but will likely show up in 2 weeks on your final exam. This is why I'm asking it. Okay, so one option, which is what Wyatt's spitting out here, which is what I said way back when at the beginning, which is okay, you just memorize. You memorize the patterns that are expected. Oxygen with 2 bonds and 2 lone pairs is neutral. Yes, awesome. Nitrogen with a lone pair and 3 bonds is neutral. Oxygen with 3 lone pairs and 1 bond is negatively charged. Right? How many of you memorized that? No. Okay. So, formal charge. How do we calculate it?
Valence electrons, shared.
Your wording makes me a little bit nervous, but that's okay. Let's run with it.
Subtract 1 pairs.
And that wording makes me nervous too. So let's take a look for the nitrogen. How many valence electrons does nitrogen have? 5. What are the shared electrons?
3. Well, bonds. I don't know.
Okay, so there becomes the problem. That's why I don't like the word shared. Okay. What I would argue is you should be subtracting the number of bonds. How many bonds are there? Minus lone pairs. How many lone pairs are on that nitrogen? There's 2 lone pairs on that nitrogen? Carefully, and this is why I would be careful in your wording, I wouldn't call it lone pairs, I would call it, and yeah, it's a longer word, non-bonding electrons. Okay? So there you end up subtracting 2, you get 5 minus 3 minus 2, and you end up with 0 for the nitrogen. Does that make sense? Okay. I think that is something that you should have memorized. Yes. Everybody, unfortunately, has a different way of spinning the language behind it, which can make the calculation slightly different. Okay. Or sorry, make how you interpret your structure slightly different, and that's where it gets confusing. So whatever language you decide to use, make sure you are damn consistent in how you apply it. Okay. And as long as you're consistent in it, I don't care what you call it. You can call it pineapples and oranges, as long as you consistently number your pineapples and oranges right. Okay? Make sense? Okay, you're like, I don't like pineapple. How do you not like pineapple? So, there's our Lewis structure. Where's the negative charge? On the oxygen. So, we've got our structure set up, our negative, our nitrogen, oxygen, lone pairs in there. So you want to put the positive hydrogen on the oxygen. Why? We're trying to deal with neutralizing the charge. So we neutralize that charge, and what do we get? Yeah? Now what? Remember, what we're looking at here is drawing a mechanism. When you think about going through a mechanism, it's not just now what I have nothing else to look at except what's drawn, or what I've got drawn as reactants. What else do I have to look at? The what? The actual the products. Right? We also have the product drawn there. And looking at the product, what needs to happen? Somehow a nitrogen needs to bond with a nitrogen. Do I have 2 nitrogens? Yeah. So, why would the nitrogen on aniline or the nitrogen on our nitrite form a bond with the other one? Which one is positive, which one is negative? We just did that right there. Both of them are neutral, yeah. That doesn't mean they don't have partial charges.
Nitrogen on the bottom would be positive.
Because
The oxygens are stronger.
the oxygens are more electronegative. And if we take it a step further, we're like, I don't really know. What could we do to help us try and find that chemistry? draw a resonance structure. And in the process of drawing that resonance, what do we see? We'd have a positive charge on that nitrogen, meaning we've now found our electrophile the nitrogen can attack. That nitrogen will be positive. We have this nitrogen now, oxygen, oxygen, hydrogen, negative, right? Does that look kind of familiar to anybody? I have a central atom that has 3 electronegative atoms attached to it. That looks kind of like a tetrahedral intermediate, like the result after a nucleophilic addition. What did I do? I took a nitrogen, which is acting as a nucleophile. I'm attacking another nitrogen, which is breaking a pi bond. Well, the breaking of a pi bond is an addition reaction. I did it with a nucleophile, so that's a nucleophilic addition. This matches the pattern of the reactions we've already seen. Yes, we're changing the identity of the atoms within it, and they're going to atoms that you may think, oh, well, those don't normally do that. It doesn't matter if they don't normally do that. They're there. That's where the chemistry is located. Find those charges. Do it. Okay? Which do you want to try and fix, the negative or the positive? Okay. How would you fix that positive? Okay. So we will get this idea, could I fix both at the same time? What's the issue with that? That's a 4-membered ring. Bad mechanistic mojo. You aren't drawing mechanisms. Arguably, they wouldn't show this as a potential multiple choice answer, so you could probably dodge that and be like, well, Mike, can I just get away with it this time? Sure, let's accept it. You can get away with it this once. Don't ever say I'm not a nice guy.
Breaking into 2 steps if you don't, it's still gonna happen, right? Same exact thing.
I don't know. Maybe. What do we still have? What do we still have? Tetrahedral intermediate. What is our tetrahedral intermediate usually decomposed to? Absolutely, guys. Good job. What we've got there is roughly the equivalent of a hydrate. What is the problem with going through and doing that? What would you be kicking out? OH minus, that's a bad leaving group. Maybe, just maybe, instead of having that oxygen pick up a negative, I had the other oxygen pick up the hydrogen. Then I would have had H2O. Because then that would have been a sweet leaving group.
So the other one would respond into the nitrogen because of that.
Okay, and we'd end up with something like that, right? But which is better at sharing electrons, the oxygen or the nitrogen? Oh, so maybe I shouldn't have had the oxygen share electrons. I should have had the nitrogen share electrons in. You're like, there's too much stuff going on. I know. It shows up prettier later. But now I've got a positive nitrogen.
So you take the H off, have the other OH picked up. That's H2O again. Or that works. It's kind of the same thing.
do you mean?
Now you have H3O plus.
Oh, yeah.
That'll react with OH.
And we'd have a phenomenal leaving group. Electrons can swing in, kick out our leaving group, and we would end up with, after a horrible, horribly drawn mechanism, our diazo structure. We now have a positive nitrogen that does not want to be positive, and it wants to get electrons. It could potentially get electrons from the outside nitrogen, but by doing so, that nitrogen becomes positive. So that's not a good idea, right? So instead what happens is that nitrogen is going to try and steal them from the carbon, right? But then I'd have a positively charged carbon, and I'm not allowed to do that. That's where step 2 comes into play in our reaction, and the copper reagent will help stabilize that aromatic structure long enough to eject the nitrogen molecule and then slide in the conjugate anion of the copper salt. Okay? You're doing a bunch of like crazy weird stuff. Okay? That's bizarre. How could all that possibly happen? That must be so neat that whoever discovered it got to attach their name to it. That's why it's called the Sandmeyer reactions. Okay? Because all of them are following under the same basic principles that we're making the aromatic ring actually act as an electrophile. And it's really coming down to that awesome leaving group. Okay? So the big deal that you need to remember, whoops, that's not the button I thought I was going to do. The big deal that you need to remember out of this is that that nitrite gets us to our diazonium. The diazonium then has a billion different things that can come out of it. And there's no way in hell I expect you to memorize all of those. But what I do expect you to do is to recognize that when you see that sodium nitrite, you're going to end up forming a really good leaving group. You've primed the ring structure to become positively charged. The next step is going to be putting a nucleophile in there. Okay? And there's a billion nucleophiles that you can use. Okay? So massive props to Sandmeyer for this, because not only did they come up with a reaction that shouldn't happen, but they came up with a reaction that shouldn't happen like 50 different ways. Okay? That's pretty cool. Okay? Questions about that? Okay, so here's the pretty part. Your textbook does a much better job of making it look nice than, of course, I ever would. Okay. But what they're going through and showing is the proper protonation, deprotonation steps for all of the pathways and how it would all work. We're under those strong acidic conditions. That's going to protonate the sodium nitrite, and that's going to cascade, get us our electrophile that can react, and we get everything coming through. Okay? And you'll notice, even as we went through and did it, we said, well, you had to put a proton on, you have to take a proton off. You have to put a proton on, you have to take a proton off. Yes, there's tons of acid-base steps. Just like there's tons of acid-base steps in all of the nucleophilic addition and elimination reactions we've been looking at. Okay? Questions about that? Okay. So, there's all our reactions. Most of these usually, or I shouldn't say most, usually you see these involved with a copper catalyst. Okay? So the copper is now involved in this to help catalyze those reactions. The cases where copper doesn't get involved is because the nucleophile is appropriately strong enough. Okay? So, moving on. There's our EAS summary. That is everything. And then we also have some kind of things to worry about. We have to be cautious about our sneaky chemistries. So sneaky chemistries, you run a reaction, watch out for acid-base conditions. Okay? Of particular concern, right through the middle, almost right through the middle. This reaction is going to be a bit of a weird one to watch out for. Why is that one going to be a weird one to watch out for as far as acid-base chemistry goes? Where's,
Adding two acids.
we're adding HCl, which is an acid, to produce what? NH2, which is a base. More than likely at the end of this reaction, we're not going to end up with NH2, we're going to end up with NH3 positive. Okay? So be aware of that sneaky acid-base chemistry coming in and messing with your overall results. Okay? So it can sneak in on you. Substituent conversions. No, come back here. Important ones to remember would be anything that allows you to convert after you've done the substitution into something else. Okay, those are going to be important steps. The new ones that we've talked about, well, even that one's arguably not new with the nitro to the amine, because that's really the reduction of a carbonyl. Okay, through, did we decide that's pseudo-Clemenson? Was it Clemenson the name?
Mm-hmm.
Yeah, that's arguably the Clemenson reagent. We've already done that. Okay. The next one, so we have one, we'll call it 1. The next one, 2, excess NBS. What was NBS?
Source of bromine.
The source of bromine for a radical substitution. Okay, we're responsible for those. NBS is that radical substitution. We need to form the most stable radical. The most stable radical is going to end up being at the benzylic position. That benzylic position is super reactive now. So we can do NBS to do substitution at that radical position. Okay? In this case, they did 3 of them. So that's one we've already seen. The permanganate is kind of a new one. Permanganate, or for that matter, chromic acid, both will do this. Okay? We've seen those reagents as oxidizing agents. The part that's new here is we didn't fully push how strong oxidizing agent they are. They are so strong that they will reduce the hell out of the benzylic position. Or sorry, oxidize the hell out of the benzylic position. Okay, so we have to remember that as our benzoic acid. And then the last one, step 4, is literally the Clemenson reaction. Okay? So all of those secondary reactions are things you've already seen. They're review. Okay? Doesn't mean you remember them. Okay? But they are review. That's the part that you need to be kind of thinking back to and looking at. The next one that's starred on here that I just couldn't fit on it is the Sandmeyer. Okay? If you form that diazonium species for the sodium nitrite, okay, that's a secondary reaction after the amine. That's where you then open up to like a billion other reactions. Okay? That tends to be less tested on because to get there you had to do 2 other steps. Okay? So usually if you're seeing questions about Sandmeyer with copper and making those linkages, it's explicitly looking at those linkages. Okay? So copper's really good at helping to facilitate those connections. Okay? So, should we just turn into a group quiz? Yes, okay. Decide on a product. So we've got 4 structures here. 1, 2, 3, 4, 5, 6, 7, 8 people. Awesome. And pairs. 1, 2, 3, 4. Does that work? Cass and Lydia? So you guys got all the numbers? So you guys are 1, you guys are 2, you guys are 3, you guys are 4. Okay? Do not talk to each other. Don't do it. Make a product. Go through it, look at it, make the product that you think yours should do. Okay? Because remember, we're doing EAS reaction, so we'll be doing a substitution. Okay? And if you don't remember what the reagent does, I'll try and flip to that slide that shows those pieces in a second. Okay? So we're going to do a substitution. I want you to just go through and pick a product that you think is it. Okay, that you think that's where the substitution is going to happen. We're exchanging a hydrogen in all cases. because it's all just straight EAS. Put the new piece on, draw that result. So you've picked a product. Okay. So everybody's drawn, hopefully, their starting material. Does everybody know what piece they need to be attaching to the structure? No. Okay, so you're three, so you can talk to each other about what piece you're attaching to the structure. Don't mess with them and tell them what the product looks like. What's the piece? Do I need to draw a piece? I could draw pieces. So 3, what's the piece? You're 2, that's right. 3, what's the piece?
That we're attaching on.
Uh-huh.
BR.
Yeah. Your piece is Br plus. 2, what's the piece? Okay. Sulfuric acid and nitric acid end up forming the nitronium ion. Your piece is the nitronium. So that's the piece that's doing your substitution. 1, what's your piece? I don't feel like drawing all that.
Carbon.
Pretty close. I'll get rid of the chlorine. There's your piece. Okay, 4, what's your piece? Just the CH3. Okay. So you all know your piece. Pick a hydrogen that you think the substitution is going to happen at. Get rid of the hydrogen, put your piece on. Don't talk to your partner about it, just pick one. So those people watching at home, I'll add the recording because I stopped the recording. Now what we went through and did is just said, okay, compare. Everybody has a different product drawn. Right? In theory? Right? Sure, saying sure like that makes me think you don't. Well, just them. I just told them they had to fix it because they screwed up. You guys just did it right. Right. So interestingly enough, in making you pick a different product, potentially, I just made one of you wrong. Potentially. Okay. So now what we'll do is move to step 2. Okay. I want you to go through the mechanism. Okay. Remember, the mechanism we talked about at the beginning of last lecture. Really, in our mechanism, there's really only the 3 sigma structures that are important. Those sigma structures are going to be the ones that you need to draw out. Okay? So to give you an idea, because Jenna's giving me an evil eye, we would take the electrons in our pi bond, and those electrons come out and attack the nitrogen. That breaks that bond. I would draw the result of that arrow pushing. What does that look like? If that is not an immediately stable structure, I will draw a resonance structure. If that is not an immediately stable structure, it won't be, I will draw another resonance structure. And I will continue to draw resonance structures until I have covered every single resonance structure. Okay? Or for some reason, somehow or another, it just magically became uber stable. It shouldn't. Okay? Once you've drawn your last resonance structure, you can finalize your reaction and take it to your final product. Okay? Draw whatever arrows you need to get it to your final product. Okay? So that's what I want you to go through and draw now. Okay? And again, we don't want to compare now because you're looking at different structures. Sam's evil black magic trick of looking at the starting material to figure out what's going on with those, on what we would expect to happen. Okay, and I'm going to pick 3 because it's easier to see because we have the charge. I have a positive charge next to the ring, so what's going to happen to the pi electrons? What's the result? That nitrogen will still be positive charge. You're absolutely right. And this is one of the reasons, excuse me, why it is a massive deactivator. But what else happened? The ring is now positive. Well, what did we need the ring to do in an EAS reaction? Donate electrons. Does it have electrons? No. So that means the nitro now has deactivated the ring. It's removed electron density from the ring. Okay? If I now say, well, I don't care that it's deactivated, I'm going to add enough heat and enough active electrophile into this to force that aromatic ring to act as a nucleophile. Where would it act as a nucleophile? Well, to act as a nucleophile, what does it need? Electrons. Are there electrons at the ortho position? No. There's a positive charge there. So by definition, there are no electrons at the ortho position, so those are gone. If I continue to do resonance, what happens? Oh, wow, I ran out of space really fast. What charge builds at the ortho position? Or sorry, para position? A positive charge. Are there electrons at that position? No, so the para can't react. So the para's out, the ortho's out, because they actually have positive. Where's the only place left that it could possibly react? The meta. So deactivators don't want to react because the rings become positive. They're now becoming the opposite of what they need to be. But if I'm going to force them to react, the only position left that has any electron density, even if it is minimal, is the meta position. That's why deactivators get you the meta product. Right? The official answer for why one product is favored over the other comes from the intermediates in the reaction. And this is that semantic argument again, right? Which Wyatt clearly didn't like. Sam was at least saying, but I know the answer. Okay? But the argument, unfortunately, comes back to the intermediates. You have to be looking at the intermediates because those structures have an existence. As thin, razor thin of an argument as that is, that's the argument. So if you're asked to explain why you get one product over another, you need to be looking at the intermediate. Right? So draw out the intermediate and look at the resonance structures behind them. Right? And what you will find is if it is an activator, you will end up generating a more stable, of course it's not up there, it was on Jenna's paper, you will generate one of your resonance intermediates as a tertiary reactivity or a tertiary stability. That makes that intermediate more stable than all the others. Everything drops in energy. That product is most likely to form. Yes?
So you're saying draw the reaction if it would happen at the ortho, para, or meta, and see when it makes a...
Yeah.
Okay.
So yeah, if we repeat that for everybody here again, what Sam is saying is that what I'm saying is that you should draw the product or your intermediate at ortho, meta, and para. So you have to draw 3 different intermediates and evaluate those 3 different intermediates for this. Yeah, I'm kind of saying that. Okay. What's your primary concern with that? Time. You're right. Absolutely. You're under a time crunch. Okay? So what you should be doing right now is drawing those intermediates out so that you trust it, so that you can rely on, yep, I can spot and see that that atom X has more electrons than hydrogen, that it is going to generate a more stable carbocation. If I react at the ortho and para positions, I'm going to react at the ortho and para positions. So that you have that as an instinct. Okay? The other option is you just memorize it. I would trust your instinct building more than a rote memorization.
Isn't it basically if you have, I mean, it's just like if you have an activator, then you
Yes, but you have to recognize what that activator is and trust that ability. And a lot of that trust comes from you having done the practice and seeing that you've gotten the answer right. If you don't trust it, then when you get to the test, you're going to forget it, and then it's not going to help.
Is it beta or ortho or para over another, or is it just depending on the activity?
Okay, so let's see, did I actually write all this out? So yeah, if we quickly kind of summarize here, atom X, if atom X has more electrons than hydrogen, We're an activator, and then notice that I'm calling it para-ortho. Has anybody done some reading on this activating para-ortho stuff? Seen it before? No? Colton, do you remember it?
What para and ortho are? But what do you mean?
In an EAS reaction, an activator activates which positions? Don't remember that? Okay, no, that's fine. The way that I was always told to memorize it was orthopara. And it sounds a hell of a lot of orthopara, orthopara. You should be memorizing it para-ortho. Why?
Paras more.
Para is favored over ortho. If you memorize orthopara, you start to put it at the ortho. Why would the para be more favored than the ortho? It's as far away from the substituent as possible. Right? So to differentiate between the ortho and para substitutions, it's now a steric effect. The electronic effect favors both equally. There's a steric effect that blocks the ortho position. Okay? If there's something already at the para, well then it reacts at the ortho.
That's all the time.
But that's the only time. Okay? The para is, and it's not a huge favoring, but the para is always favored over the ortho. Okay? So what if you want something to go to the ortho?
Substituent at the
Put a substituent at the para that you could remove, like, we can't remove bromine. Not a bad try, but no. There was only one reaction that I said was reversible. I knew you were going to say that. The issue with the hydrogen is that's reversible after like 5 steps. There's one that's directly reversible. Do we have the summary right here? Son of a, it's not reversible. I didn't fix it on this slide. Dang it. I said son of a. I can't finish it. The sulfuric acid one, the sulfate, is a reversible one. That's the one that's reversible. So you could put a sulfate on, and then you could take the sulfate off after you ran the reaction. Okay? So, directing effects come back to activating and deactivating, which is really based off of those. Okay? What this slide was set up to do, in fact, I think it's the next one, what I'm showing here is exactly what Sam wanted to do. Look at the resonance contributors from the starting material to predict reactivity. Again, absolutely fair game, but that's not the official party line. Okay? So I just want you to be aware of that. Go away, go away, go away, go away. Come back here. Okay, here's the one I want you to hit me up on. Okay, we'll erase some of that. We don't want to, mislead you anywhere. Because you know me, I never mislead. What are we specifically looking at in this case? Halogens. Do halogens have more electrons or less electrons than a hydrogen? More electrons than hydrogen. So that would mean we would expect the halogen to be what? An activator or a deactivator? Activator, because it has more electrons than hydrogen, right? So by having more electrons, those electrons should donate down to the ring. Sweet, that's an activator. Okay? The result of that being what structure? With a negative charge on the ring, right? I don't have any problem with that. Let's actually draw a halogen there. Anybody have a problem with that structure?
Yes.
Oh, yeah, what's your problem with it?
Double bond with CL.
I have a double bond to a halogen. Am I allowed to do double bonds to halogens? Officially, yeah. But no. No, that's not nice. Halogens don't do that. Okay, why would they not do that?
They're electronegative.
Our rule is that they're electronegative. They would withdraw electron densities. So if it withdraws electron density, though, now what happens? If halogens are more electronegative, they take the electrons from the ring and they draw them outwards. Meaning, the halogen would actually be a deactivator. So depending on our interpretation, we get two different answers. Really? Yes. So, what is the answer? Not to give away any kind of like clues. I don't know, I'm just drawing a bunch of lines now. They are para-ortho directing, which would make them, but why did I show blue lines? Halogens are deactivators. I don't know how you guys didn't get that. But they're para-directing, para-ortho-directing. Okay? You're like, there's a crossover between, yes, there's a crossover between them. How many crossovers for EAS are there? One. It's the halogens. Everything else, it's just resonance. Okay? So that's a pretty sweet system within EAS. If you have multiple, a complex aromatic ring, just run the substitutions or run your resonance to predict where the charges build. Do your substitution at that position. Okay? If it's a deactivator, you should be doing it at the meta position. If it's an activator, you should be doing it para-ortho. If it's a halogen, you have to remember that the ring is deactivated, but it'll still direct to the para-ortho. Okay? It's directing to the para-ortho because it has the electrons to be able to kind of activate those positions. It's a deactivator, though, because it's not willing to make that share. Okay? So it actually has to do with orbital alignment within the system, and it's that orbital alignment that kind of is what's making that weird crossover. Okay? After that, we just have some kind of weird stuff to talk about that I would love to just continue to just burn through, but unfortunately we're kind of done, so sorry. So we'll come back to the Friedel-Crafts alkylation and acylation on Monday, and then we'll look at probably the NAS stuff.